Jadi mana yang Michael, sini Bang. Aiman Michael.
Gak bisa ya?
Michael, ngapain Michael? Remote is gone. The remote is gone, Michael. Stand up, Michael. I'll press the button. Sit in any of the desks? No?
No, Justin no.
Sepaket telat. Pas jalan. Pas jalan apa pas dari jalan FM itu. Ya, siapa tahu beli kopi dulu. Okay, we'll need someone to
Gerak ya. Lu aja dah. Lu aja, lu nyampe kok. Ji, harus jatuh Ji.
ya. Benerin. Oh, okay. Can you? Kenapa? Okay. Can you send me an email, carbon copy my secretary, and then I'll to me and my secretary. CHIMPEYA. You know? Yeah, I know. Right. Udah jam tidur langsung assume hold on, I think it's wrong one.
Dia permisi ke motor dulu, motor minggir-minggir dulu buat dia buka pintu.
It's okay, foreigner. Dia foreigner apa expat? Expat? No, you're immigrant. Illegal expat.
Ngeliat kan, gue kira kan mungkin memang dia apa sih berlihat aja gitu. Soalnya kan menurut soalnya emang
Okay, forgot where I put my pretest, but I think it's still in Socrative. So go to socrative.com. So Socrative, Socrative. Okay. Socrative.com. And go to room. Okay, go to socrative.com. And then room is SGUMD 2026. And just wait for me to launch the pretest. Oops, hold on. I haven't edited. Yeah.
You completed the project.
Okay, I launched the multiple choice pretest. Go ahead and do that. Oh, okay. Mungkin ke depannya ditulis aja kali, dikasih label ya. Put your name as the same as SGU registered name. Okay, so I can match. So put your official name, in other words. The pre-test is not graded. The post-test will. So this is what we will discuss, and then at the end of the class, you'll do exactly the same test, and that one will be graded. Okay? So it's kind of a warm-up. Learn about it, and then review. free to screenshot the quiz so you have something to review while we're going through it.
But later, there's going to be the exact same quiz
Uh-huh.
for the post-test exam.
Yeah, you will redo exactly this, like 2 hours from now. PowerPoint is already posted in Google Classroom. Okay. Everybody did the attendance? All good? Okay, I'm gonna close the form.
Feeling those old like PT stars. Yeah, when you hit something, you just get washed out of the car. So they have an automatic detector.
Oh ya, sekarang yang paling saya ingin yang paling saya suka itu April. Kemana sih saya upgrade yang ini shop untung saya pakai yang ini yang double type tapi sekarang dua nah, saya nggak bisa jadi harus belajar ya bisa sih sini biar dekat sama orangnya saya semakin terus nih biar habis-habisin aja.
Okay. Sorry, I have some administrative things I needed to do. All right. So we're now on to our first topic, Scott Chef assemblies. Remember, I told you that everything, pretty much, most things, machines, have shafts, right? Because the power generated is in the form of rotation. It's just practical. And electric motors, yes, there are linear motors. Motors that literally just move things on a straight line. But again, it's very specific application, right? For example, you are launching an object, a ballistic bullet, for example. There are like linear electromagnetic cannons that literally accelerate a bullet or the ballistically launch an object to shoot, right? Without gunpowder, you use electromagnetic motors and propel it. So, you propel it once, that's it. But in practical everyday life, you wanna make something, you wanna grind something like your coffee grinder, right? I mean, most things in life, you just need continuous motion. Cars, and so everything, most power takeoff, basically power generations, then the output is a rotating shaft. And so shaft becomes the center point of our discussion in machine design, right? So this is an example shaft and joints between shaft and something else. So this is a shaft. This is called a spline. We'll talk about that further. Okay. This is a thread where you can mount things like maybe a fan, for example. So think about an example, a very simple example. No motors, just mechanisms of a bicycle, right? We have obviously shaft here to roll. You know, one of the earliest invention, the wheel. Right? The wheel basically provides locomotion. It's basically the invention of a vehicle rolling on something round. Way back, somebody thought of it. And the shaft becomes the crucial point. You ever saw the animation of Egyptians pulling a big, huge rock? They put little rods on the floor that, you know, the big block of stone basically rolls on it. I mean, that's a wheel, right? But that's basically not a wheel, it's a shaft. It's a shaft. And so shaft becomes refined to a point where you mount these on bearings. They are very low friction. You remember during COVID there is this fidget spinner. you hold the middle and then you spin it. There is a weight on it, basically a flywheel, right? You spin it and then it spins for a long time. Very low friction, right? Ball bearings. So a shaft, essentially something like that. If you can feel any motor or any shaft mounted on bearings is like that. We're trying to create a situation where the shaft, powered or unpowered, in this case the wheels are unpowered, they can rotate freely with very low friction. That's the idea of a shaft with bearings. In the case of the wheel, then it's just floating. It's just a floating shaft. It's not powered, right? We're not putting power into it, unlike motorcycles. We put power here, but the wheel itself is unpowered, especially the front ones, just floating. So we have shaft on bearings, ball bearings, shaft on ball bearings. Here is our source of motor, right? Motor, locomotion. Our pedal, the pedal itself actually have a crank arm with bearing at the pedal because the pedal stays flat. Yes. So you want bearings in order for you to put load but not increase the friction. This is called a bottom bracket among bicycle terms. Big bearings there because that's one of the main loads, right? You step on it and this has to sustain the radial load. And we will also use this terminology, and you gotta get used to it because we're gonna use it a lot. So if you have a shaft, okay, this is the axis, right? So load in this direction is called axial load. And load in this direction is called radial load. And these terms are standard. So whenever we say axial, radial, I expect you to understand what that means. The easiest way to remember it is, this is along the axis, and this is along the radius. Radial, radii, radius. Okay? So if this is a circle, right? This circle, that's the radius, and so this is a radial load. Okay? So anytime you have a shaft, this is all radial. And then you have the post. The post is not exactly a shaft, it's just a sliding rod, I guess. Okay? Let's see. Well, there is some mechanism here, and there is a shaft. Even though it's not rotating continuously, the hinge on the derailleur here, you know what that is, right? It's to shift the chain and sprockets. There are some pivots. There is also a shaft here on the extra sprocket. The brakes, if you think about the clamping of the brake this way, or if it's this way, there's also a rotating point. So this is a typical mountain bike brake is like this. It moves in, right? It clamps the wheel or the wheel. This is a pivot point. It's also a shaft. One of the parts you want to lubricate when your brake starts to not spring back. You know how it is. It's stuck closed. You don't use your bicycle for a long time. Rain got into it. No ball bearings, just bushings. Gotta lubricate that. Okay, the steering post, the front set. Now, why do we need bearings here? I mean, it's obvious why we need bearings here. Why do we need bearing on this one? Yes, you have motion, but here you don't put a significant bearing set to sustain the load. Why? What kind of load are we talking about here? Axial load. Very good. You're using the right term. So here, what kind of load is it? Radial load. Because the shaft is in this direction. Yeah? It's into the shaft is into the screen and the load is this way. Along the radius. Here, the shaft is this way and the load is along the axis. Okay? So there are what is called the thrust bearing. We'll talk about bearing next week. There are thrust bearing here, and on the top, so the headset has ball bearings. When you have a lot of load and you want very low friction, then you do a ball bearing or roller bearing. But something like this, very low motion, the hinges, very low duty. You don't use it all the time. It's not rotating all the time, like your wall fan, for example. It's rotating all the time. This is not, right? I mean, it's mainly static. The brakes are most of the time static, and then sometimes it rotates. So you just need a pivot point. That one you don't use a ball bearing. You use just a plain bushing. All right. Here is the exploded view, right? This is the shaft. That's where your bearing comes in. Then your shaft goes into the inner race. You look at cars, many shafts, right? The axles, the engines. This is called a drive shaft or axles. It's called a drive shaft because you drive the wheels with it. And of course, you gotta have bearings here. You gotta have bearings there. This is the center shaft from the engine to the back. Oftentimes, you also have center mounting there, universal joints. So, a shaft is a method to deliver power. Think of it that way. Inside this engine, there is this main crankshaft. Okay? That's the source of power. And it is also supported by bearings. Very different bearings though. It's called a hydrodynamic bearing. So if this is the shaft, you basically have two halves of semicircles capturing the bearing, capturing the shaft. And in between that, you basically have oil suspending the shaft. So this is flowing with oil, pressurizing the cavity, so the shaft actually floats on pressurized oil. It's also a bearing We call it hydrodynamic bearing. We'll talk about that next week. Okay? Many joints on the suspension is also, you can think of it like a shaft, even though similar to the brakes in bicycles, it's basically a pivot, and you put bushings on it. And they put rubber around the bushings, so you basically, so if this is the arm, okay, so the suspension can move up and down with the spring, and this is the lower arm, it can pivot like this. There's a pin here too, or a ball joint. They move up and down, and think of it as a shaft, even though it's really a pivot. Look at industrial machines. There are shafts everywhere. These things are supported by rollers. Okay, there is a shaft here with a roller. The roller is on bearings. And when we want to move this conveyor belt, then there is a motor that actually spins this shaft, and therefore the whole belt moves. These entire rollers, they're all on bearings. They're basically shaft on bearings. So this is a typical conveyor belt. Any automation, you'll have this. This guy is the motor. That's the arrow pointing to the direction of the conveyor belt. And so here you have a very simple mechanism, not simplistic, but simple as in. Okay. So this is the motor, pulley, belt, and this thing is a bearing. Okay? It's captured with something called a pillow block. So it's basically a bearing, but it's captured inside this case. This is called a pillow block. And there is a bearing inside. So this is the shaft of the roller. It has bearing here and a bearing here, right? This is the pillow block. Looking from the side. Looking from the side, there is a mounting point here. Okay? And therefore, this shaft is under load. Tell me, what kind of load is it? So if this is a roller, right? This is a belt going around. The conveyor belt. I mean, here's the tiny belt for the motor. So the motor is here. Belt, pulley, and of course this is the roller holding the belt. Roller, bearings. What kind of load are we looking at here?
Radio.
Due to what? Okay, the object on the conveyor, sitting on the conveyor belt, the big belt. The big belt itself actually pulls on this guy, right? Do you see that?
Yeah.
So this is the roller, the other roller. Then you put the belt around it. So the belt has to be in tension, of course. Otherwise, it's falls out. So because of the belt is in tension, then it creates a load this way, right? So you basically pull on this roller, and the roller kind of holds the belt. And therefore, if you look at the shaft here, looking from the top, then you will have supports here and here. That's the bearing. I'm drawing this picture here. Okay. In fact, let me draw it there. Okay, so you have this roller being pulled by the belt, the big belt. So the roller is being pulled by distributed load like this, and the support actually supporting. Okay? So if you look at it from the side and draw it two-dimensionally, this is my shaft. It's basically supported by bearings and being loaded this way by the belt. So this is the distributed load. This is the reaction load, right? RA, RB. It starts to remind you of statics and strength of materials. Yeah? So we are actually taking what you've learned in strength of materials, now applying it on machine elements. Because this is the practical application of what you've learned in strength of materials. So, does that make you regret less that course? Do you think that course is hard? Strength of materials?
Not necessarily.
Okay. It's not that bad, right? So you have a shaft under load radially, and you got the bearing supporting it. Now, I want to discuss a further concept. Yeah, let me talk about it now, because we're on it. So, look at the shaft under load like this. And keep in mind, the shaft is round. We're just looking at it from this side, so it looks rectangular. But it's a round piece like that. And this shaft is rotating. Okay, so this is the shaft. It's loaded from the top. It's supported at the ends like this. But it's rotating. Now, if this were not rotating, what kind of load are we looking at in terms of, remember, strength materials? The types of loading, you have axial, you have bending, you have shear, you have torsion. What are we looking at here?
If it's not moving.
If it's not rotating,
It's not moving.
it's bending, right?
Yeah.
Like this.
Yeah.
FYI, axial loads usually are not too concerning. You will not fail or break anything by axial. Try to pull on this, and break it axially. It's very tough. If you want to break this piece, how would you do it? Bend it, right? So bending is usually the most concerning load in machine design. So bending, it's under bend. It's bending. So if I draw the deformation of this, it's like this, right? Exaggerated, of course. Now, is this always bent this way? What will happen if this shaft rotates? So it's bent this way, right? But then it rotates. So what happens to the shaft? Right? It's bent this way, but then it rotates. Okay? So it's time to imagine it, right? Let's say this is a planet. Okay, this is a planet. And I'm sitting here. Okay? And what's your name?
Michael.
Michael? And you're sitting here. Okay, Ivan, you're sitting here. And this thing rotates. At the first place, what am I seeing when I'm sitting here? I'm under compression, right? This is compression. This is tension. So what both of you are seeing on the ground is that it stretches, right? It stretches. But from my point of view, it's compression, right? So it's compression here and tension here. But what happens when this planet rotates 180 degrees? Now I'm here, right? So after it rotates, the situation, I am now bottom and you are on the top. So what do you see? Now you see compression and I see tension. So if you think of the shaft as an object composed of many different elements or points or material, what does the material see? So if I take a square here, okay, and I am the square, if I'm a part of this shaft, I'm stretched and then I am compressed, and then I'm stretched again and compressed again. So on the rotating shaft, you are actually seeing a fluctuating load. So you're no longer seeing, I mean, we draw it statically as if this bend is always like that. Well, it is, but because it's rotating, if you think about yourself as part of the shaft, you're actually doing this. Right? And have you ever played with a paper clip? Anybody has a paper clip? No? If you ever played with a paper clip or a thin piece of metal, and then you bend it one way, you bend it the other way, you bend it one way again, it's going to break. But it didn't break on the first cycle, isn't it? The first time you bend it, like this much, say, whatever, 20 degrees, right? You bend it 20 degrees, it doesn't break. You bend it the other way, 20 degrees, it doesn't break. You bend it the other way again, still hasn't break, and then after like 5 cycles, it broke. So you see that fluctuating loads actually is more dangerous than static load, and you have to treat it differently. So something that will not break the shaft under one load and static will break it if it rotates and it fluctuates. Okay? So if you look at the load, it's actually like that. Okay, so this is the stress and this is time. So as this shaft rotates, it goes from tension to compression. Negative, right? This is negative, this is positive. So positive stress, negative, positive, negative. I know there is no such thing as positive stress for college students, but I'm talking about tension and compression. So you're doing that. And this can create failure, premature failure, that you thought, hey, the material can sustain 600 MPa, megapascals. Why is it failing at 400? Well, because it's fluctuating load. So we'll learn the calculation next time, or if we have time, maybe we'll start something off today. Okay? But that is the kind of calculation that we have to do for shaft. So back to practical applications. So I'm kind of introducing, I'm a bit ahead of myself there. But back to the application side. This roller has also needs some adjustments, right? Because this belt can stretch. So the roller, to create the tension, you need to push it that way. And this rod, or threaded rod, will give you that adjustment. So that's 2 simple examples, right? Bicycles and conveyor belts. Now, if you think about drive systems, and again, we're still at the big picture, 30,000 feet view here. You got the source of power, you got some transmission or transfer elements, and then you got the load, right? You got the source of power. It can be an engine. It can be a motor, electric motor. And then you have some ways to transmit the power. Maybe there is no transmission like a car transmission, but you know, two shafts joined with couplers. That's a transmission. It's transmitting power, right? So you still need the coupler. We'll learn about shaft couplers. And then at the end, you have a load application. It can be a mixer. It can be a cooling fan. It can be a wheel. Right? Anything. It can be the excavator arm. What else? Right? Many, many applications. So every shaft assembly, you can think of it this way. A motor or source of power, a shaft, and the load. In this example, a fan. And the shaft has to be supported by bearings. Exactly 2 bearings. Exactly 2 bearings. Can anybody tell me why? Not 1 and not 3. Why is a shaft supported by 2 bearings? Anybody want to take a shot? Hmm? What happens if you only have 1 bearing? Why is it unstable?
Due to the baseline, it causes vibration.
Okay, well, I mean, it's still staying. It's still there. Why does the vibration invention happens?
It's supported on one point.
If I have a situation like this, okay, hold this with 2 fingers like this. Okay, I'm gonna press. Resist my load. Okay, what do you feel? What do you feel? You are the bearing. No matter how much you clamp, it's just very hard. I mean, I can hold it with my 1 finger, but once you put the load on it, you have no way of reacting. Draw me the free body diagram with 1 bearing. Strength of materials. Is it like this? No, because it would not be in equilibrium. The truth is, it is still in equilibrium if I press on it. I mean, see? I mean, it's not falling down. So what happens to my finger? What is my finger doing? It expands because I'm not strong enough. Let me draw the bearing a bit bigger. Okay, so you have the ball, you have the inner race, you have the outer race, because a bearing, you have the inner race, and then you have the outer race. Okay, this is the outer, this is the inner, and this is the ball in between. Okay, so the inner can rotate with respect to the outer via the balls. So outer, inner, inner, outer. So I'm cutting the shaft, right? So what happens if I put the load F? I need to counter the moment, right? So how does this guy counter the moment? How will the arrow be? Where is the reaction force? I'm zooming in for the purpose of looking into the width. So I cannot do these two arrows collinear because then it would not resist the rotation. In order for the moment to be countered, my reaction would be here and a little bit to the left, right? In fact, it will be on the opposite extreme. And so the bearing is actually under rotation, and that's what you feel, right? Your finger is kind of twisted. I mean, your finger is twisted. Exactly, this bearing is twisted. This one, because but this is in equilibrium, right? RA, RB, F. You can do the math on this. If you do the math on this, what kind of numbers will you end up with? If this is 100 pounds or 100 newtons, what kind of numbers are you going to see here? Thousands, okay? Thousands, if not like tens of thousands. And that's why you cannot resist even a tiny load on this end of the pen, right? Your finger cannot resist because this has to be 10 times stronger than whatever I push. So this is in terms of 1,000 Newton if this is 100 Newton. And that's why it's going to break. So that's probably an easy answer. The best explanation I can give you why we don't have one bearing. Even though it's intuitive, you don't do one bearing. But trust me, you will do it when you do your mechatronic system design. I've seen students do it all the time. Okay, they have one motor, this is the wheel, and they just put one bearing. So don't do that. But why not 3 bearing? Isn't it stronger? Why not 3 bearings? And this is where real world aspect starts to come in, right? The X means that. Why not 3 bearings? Too stiff. What do you mean by that?
Within the two, it allows the shaft to like vibrate a bit, so there's not much pressure on the shaft.
Okay. Figure. Okay. Cost, sure, but let's say cost is not an issue. Let's say this is for a very important machine, so I don't mind spending a 3rd bearing. Let's go back to the situation where you only have 2. Let me erase this. So, in reality, there is something called tolerance. Anybody know what that means? What does tolerance mean?
Marginal error.
Error, right? So when I mount these 2 bearings, do I want them in one line, in the horizontal plane? Yes. Will I end up there? No. Okay? In the real world, there is no such thing as perfect precision. Is this table flat? Well, yeah. Plus minus, right? Is this table collinear with this? Is it on the same plane? I mean, you can see it here. It's not, but even if you make it as parallel as possible, there is still called tolerance. This pen, are they the same diameter? Yeah. Give or take, what? 1%? 0.5%? So there is always a certain tolerance in the real world. Even a 1 meter length ruler is not 1 meter. It's 1.00001, right? No such thing as perfect. So, real world tolerance will make my bearing mount I'm exaggerating, to be like this, right? It's offset from this bearing. So I want it to be precise. I want it to be precise, but in reality, it's like this. So what will happen to the shaft if this bearing is actually shifted? Well, the shaft says fine. I'll adjust with you, right? I'll adjust with you. But there is no load. There is no extra load happening because if you, okay, hold this with two hands like this. Okay, so if this is shifted, right? You're not, the shaft is not undergoing an extra load. But what happens if I add a third bearing? What happens if I add a third bearing like this? It's going to force the shaft up, right? So if I accentuate it, the shaft will have to do that. Of course, this is exaggerated, right? Two bearings has to be collinear. And here goes the math. If I draw 2 points, can I draw a line that passes both points? Of course. It's a line. Straight line. But if I have 3 points, can I draw a line that passes all 3? Yes, if it's perfectly collinear. Perfectly collinear. But if not, then one of them will be out of place. And what will happen to my shaft? It's going to have to be forced. And you're introducing a very significant load. Very significant load. And so, that's why you only have 2 bearings. Yes?
Do you think that this explanation refers to like one particular type of bearing? Because let's say like two examples. The first one is an engine. It has multiple.
Oh yeah. Yes. I'm referring to a rigid ball bearing, not a hydrodynamic bearing, because a hydrodynamic bearing can vary in terms of its film thickness.
And then the next example is, let's say from an engine to the differential. So from the transmission itself, you have a bearing, and then in the middle you have the propeller shaft bearing, and then at the end you have the differential bearing.
Mm-hmm.
But all the 3 bearings is normally not the same, but it still consists of 3 bearings.
Are they one bearing? Are they one shaft?
No, usually it breaks in the middle.
And then you have something called a coupler.
Yeah, it's a bearing. Yeah.
A coupler is not a bearing because a coupler actually allows some misalignment. So this motor actually has a bearing. So what is not drawn here? Right here. So this is why. Okay. This is why you have couplers, because this shaft takes care of the load, and this shaft belongs to the motor. Inside the motor, there are bearings.